We're going to continue talking about the wave-particle duality. We ended last class period with a slide that was asking about, I think it was which things showed particle behavior. We've seen three things that show particle behavior. That is, they can only be explained by a particle theory. We had the photoelectric effect, Compton scattering, and for some reason, the last one, oh yes, X-rays. There are more. There's particle production, pair production that is a particle theory thing only. So there are things that can only be explained with the particle theory for light. But then there are things like what we did in lab with the interference experiments, with polarization experiments. Those can only be explained with light behaving as a wave. And so we have ourselves, I think she left her jacket. We have ourselves a bit of a pickle here in that we have some things that can only be explained with one theory, some that can only be explained with another. And so scientists have to decide, how do we come to grips with this? Now, personally, I think this means that we don't really fully understand light. That there is something fundamental about light that we still don't understand. But for now, we take what we call a complementarity approach. We say that light has two natures. You know, we can talk about the nature of my car. It's a gasoline engine, so that's one nature. And it's a front wheel drive, that's another nature. And some things, you know, if we talk about, well, you know, how much power does it have? Well, that's going to be something that has to do with the gasoline nature. And if we talk about, well, how well does it handle in snow? That's going to be a front wheel drive nature. You know, so we have the same type of thing with light. We have its wave nature and its particle nature, and the two complement each other. And when we're analyzing a situation, we just have to look to the right one for the specific type of situation we're analyzing. But now we're going to move on from that to talk about something completely different and yet the same. So we start by just reminding you about the double-slit experiment. Double-slit experiment, you have two slits, and light goes through those two slits, and then you put a screen behind it. And on the screen, instead of seeing two spots, one for the left slit, one for the right slit, you see a whole bunch of spots. And we call that a diffraction pattern. The only way that can occur is if the light wave goes through both slits. Goes through both slits and interacts. It can't be explained as particles. So, sticking with the light wave, well, I have to have this here as an interlude. We're going to now start talking about particle wave duality of things that aren't light and quantum mechanics. And so I have here a couple quotes that to me are very compelling quotes. The first one is really important, especially for people who are just learning about quantum mechanics. And that is, anyone who has not been shocked by quantum mechanics clearly didn't understand quantum mechanics. It doesn't make a lot of sense in many regards. To go a step further on that, we don't even have a fundamental theoretical basis for quantum mechanics. We have a conjecture basis for it. That's not the way scientists like to be. They don't want to be, well, I think this is it. But quantum mechanics does give us correct results, and that's why people use it, even though it's not based on solid theory. And then we have the quote from Richard Feynman, who's reasonably famous. His biography about him is called Genius, or his name Genius. I'm going to tell you what nature behaves like. If you will simply admit that maybe she does behave like this, you'll find her delightful, entrancing thing. Yeah, that's a good gift of trying to make things sound great. So we're going to talk. That 7's not supposed to be there. I don't know what's going on. Clearly, I was doing something and not thinking. Probability. Quantum mechanics, it turns out, is based on probability. And to get us to that point, we're going to talk about the double-slit experiment with light going through two slits. So I have two slits, and I have a wave that travels through those two slits. And then that wave interferes if I set up a light detector that is something like film or something like a charged coupled device, a CCD, like you have in your camera phone, that's measuring photons. The CCD device is essentially using the photoelectric effect to measure, oh, a photon hit here, it ionized an electron and kicked it out, so I have a new charge state. That's what it's doing. So it detects photons. So you have waves when it goes through the slits, but when it gets to the screen, it's a photon. And that photon will, each photon that comes to the screen is only going to be measured in one place. So if you just had one photon go through your double slit, of course, it was a photon before it goes through the double slit, it's a wave when it goes through it, a photon after. It only hits one place, you don't see a pattern. But if you keep shooting photons at it, over time, you're going to have a pattern. But you cannot say where the photon is going to light up your screen beforehand. You can only talk about the probability. We should have a diffraction pattern that looks something like this. And so the place where it's the highest peak, that's where it's going to have the highest probability of the photon hitting. The places where it's at a minimum, there's zero chance of the photon hitting there. And so we can talk about the probabilities of where the photon will be found based on the wave function for the light. Does that make sense to people? Because it's an important philosophical idea to lead us into quantum mechanics. So with that probability idea, let me skip over here. The probability is proportional to the amplitude of your electromagnetic wave squared. So the probability is proportional to the square of the electromagnetic wave's amplitude. That's going to be important to us. We're going to try to find a wave function to describe something like an electron. And then if we square its amplitude, we'll say that should also tell me about probability. And all of a sudden, it sounds weird. A wave function to describe a particle. I have a BB flying through the air, and I'm using a wave function to describe its motion. That's what quantum physics does. Now, let's look at what I skipped over here. The intensity of electromagnetic wave is the energy per time per area, and that is proportional to the electric field squared, is all I was saying there. And then we could say, well, the intensity is also the number of photons per time per area times the energy per photon. And so that's showing us the relationship between the probability of finding a photon and the, I don't have it there. The probability of finding a photon and the amplitude squared. So to make sure that people have been following along, what aspect of the electric field, the wave function, gives the probability of finding a photon at a local position, at a given location? Okay, James, Brandon, Michaela. That would be all the people in one row. Oh, and Angela. All right. Okay, we've got ourselves some issues. We have 5 people who did not understand what I was saying or didn't hear the words coming out of my mouth. The people who said amplitude, I can understand that because it was related to amplitude, but it is the amplitude squared. right? The electric field squared, the amplitude of the wave function being the electric field, is what the probability was proportional to. The frequency was not part of what we were talking about. The intensity depends on frequency, but the frequency isn't changing with location. So it was just the square of the amplitude that was our important thing. So if you didn't answer that, make sure you understand why. Because otherwise quantum mechanics is completely lost on you. 1923, Louis de Broglie was writing his PhD dissertation. Dr. Phillips was talking about getting a PhD. Back in his day, a PhD dissertation might be 20 pages long. These days, a PhD dissertation is going to be minimum of 200 pages long, probably twice that. It'd be good to have the smaller amount, but at the same time, those guys were geniuses. Those guys, first of all, they had to study all the sciences. They weren't just studying physics. And second, the math they did still makes me quake a little bit. They were really good. Anyway, so he's writing his paper, and he throws in there a conjecture. He says, well, look, if light has a dual nature, if light is both a wave and a particle, and we just have to choose the right one to describe each situation, then what makes light special? A lot of people could give an answer to that. Well, light has no mass. That's special. Nothing else has no mass. Well, nothing else except for a couple other gauge bosons. Like a graviton has no mass. But light has no mass. But he said, shouldn't other particles also we should be able to treat them as waves? If we can treat light as a particle or wave, we should be able to take other things that we treat as particles, like Corso, and say, I'm going to treat Corso as a wave, and figure out what's going to happen with Corso just using wave physics instead of using particle physics. That's what Louis de Broglie proposed. Yeah. I figured you'd be back before you cited the water.
Thank you.
So Louis de Broglie says, I'm going to propose that the same relationship we had between wavelength and momentum for a photon applies to any particle. So that means I could take something like Corso. Say, okay, Corso's walking at 1 meter per second, and he has a mass of 100 kilograms, so his momentum is 100 kilograms times meters per second. I'm just making numbers up. So he has a momentum of 100 kilogram meters per second. What's his wavelength? Well, somebody do that calculation for me. You can do it in your head. If Corso's momentum is 100 kilogram meters per second, what is his wavelength? According to de Broglie. Or actually, you know how to pronounce his name? Of course you don't. De Broglie. What's 6.626 times 10 to the minus 34 divided by 100? 6.626 times 10 to the minus 36. So Corso's wavelength times 10 to the minus 36 meters. Put my fingers that far apart. I can't get them that close together, right? 10 to the minus 36 meters is an immeasurably small wavelength. So we can treat Corso as a particle. The thing is, the wavelength for Corso, unless he is absolutely still, is going to be so short that we're not going to see any fundamental wave behavior. We can have Corso run as fast as he can through the doorway. He's going through a single slit. If he is a wave going through a single slit, what's going to happen? He's going to diffract. He's going to spread out. Do we worry about Corso running through that doorway? We don't. Because his wavelength is so short, we learned that the first diffraction minimum is going to come at d sine theta is equal to the wavelength. Well, if his, I forgot the wavelength there. Yeah, no, I got it right. The doorway is about 1 meter wide. So we don't have to change much here. 6 times 10 to the minus 36 is what sine theta turns out to be. Means theta has to be approximately 0, right? It's on the order of 10 to the minus 36. How far does Corso have to travel for us to actually be able to see that, wow, there's a millimeter separation between, Corso's center and the fuzz we see on it? It's going to have to be outside of our solar system. So we don't worry about Corso's wave behavior at all because this wavelength is so short. Okay, what?
I've never heard my name that much.
Sorry. So what kind of particles is this going to be useful for if it's clearly not useful for Corso? Really low mass particles. Because really low mass particles are going to have really small momenta, which means their wavelengths are going to be longer, and we might actually be able to see some kind of wave behavior. So quantum mechanics, remember I worked to disabuse you of the idea that quantum mechanics is the physics of the small, right? Because it's the physics of treating things as waves. But its differences are only seen if it's really small, because that's the only case where you have a wavelength that's long enough for you to actually see a wave behavior. So that's why people call it the physics of the small. So let's go straight to some examples to illustrate that electrons actually do follow de Broglie's idea. Right? De Broglie comes up with this idea, his hypothesis, and in the scientific process, you have a hypothesis, you have to have experiments that would test the hypothesis and potentially disprove it. So one is, the first one here, let us send electrons onto a surface. Now, that slit there makes you think that we're diffracted through that slit. We're not. It's just a mass so that we have a narrow beam. We have the electrons hit the surface, and then we're going to look to see what direction we have scattered electrons. So Davisson and Germer did this experiment. You might notice. De Broglie came up with this idea in 1923. When did Davisson and Germer start their experiment? 1923. They said, let's check this to see if de Broglie's idea holds any water. And what they found was, sure enough, at an angle of 50 degrees of backscatter, they had the maximum amount of electrons scattering back, which agrees with, and I have it here, which agrees with Bragg's law, which was actually not yet developed at that time, for diffraction that you should have from a crystal, if you have the same wavelength that de Broglie predicted. So their experiment confirmed de Broglie. Now that's only one experiment. In lab, that's pretty much all we did because, we didn't have a lot of time. But with a lot of time, you do more than just one experiment to confirm. You go back, you say, well, let's test another prediction. So another prediction, George Paget-Thomson studied what happens when you have electrons scattering off a powder of crystal. You take crystal, powder it. And if you have light, and he found that you had concentric circles in both cases. And once again, the patterns agree with the Bragg scattering prediction. So another case of looking at diffraction. Finally, or at least finally for me, is repeating the idea I started with. If you have light waves going through a double slit, you're going to build up a diffraction pattern. So if you have electrons going through a double slit, if electrons are behaving like waves, then you should be able to use the de Broglie wavelength to calculate its wavelength and calculate the diffraction pattern. And now with photons, it's kind of hard to shoot one photon at a time. With electrons, not so hard. And so now this is clearly a computer-generated picture. The first one I had, I believe, was actual data, the one in the opening slide. Even if it's computer-generated, the experiment has been done multiple times. You shoot one electron, you got one spot. Shoot a couple, and it looks like a uniform distribution. But here, up to 40, you can start to see that there's some banding. 200 electrons, very clear that you have banding. you get to 2,000 electrons, and you're like, well, yeah, that's exactly fitting the intensity that you would expect if I was sending light waves through with a wavelength equal to the de Broglie wavelength. So yet another experiment. All of these experiments, by the way, were diffraction experiments, but testing in a different way, showing that the electrons are behaving as waves. And you can change. Now, what do you have to do to change the wavelength of an electron? The wavelength was, I'll write it here. Wavelength is h over momentum. So what do you have to change the wavelength? You got to change the momentum. You got to change the speed. So if you make it go faster, you can have a bigger momentum and thus a shorter wavelength. Make it go slower, you have a lower momentum and a larger wavelength. So with this experiment, you can shift the wavelength easily just by accelerating your electrons more or less, and you see the pattern shift. Another way of testing to make sure that de Broglie's equation is the right one. Now this one here is an interesting, we're clearly not going to be doing experiments on anything in quantum physics. But if you're able to count and detect which slit a photon goes through, you should be able to match up. A photon goes through the left slit and makes a spot here. A photon goes through the right slit and makes a spot here. But you know what happens when you do that? At the slits, you're forcing light to be a particle. You're not allowing it to be a wave if you're measuring which slit it goes through. And you no longer have a diffraction pattern that appears. That's one of the crazy things about quantum mechanics. When you make a measurement, you fundamentally change the system. And so making a measurement of which slit the light went through forced it to go through either one slit or the other instead of going through both. And it fundamentally changes then what happens, because now you don't have a wave going through both slits, you can't make a diffraction pattern. Once again, that's something that's been actually tested experimentally. I wish we could do all of these experiments, but yeah, not so easy to do. And not the kind of thing you're going to do in one class period or one lab period, or one semester's worth of lab periods probably. Here is a common application for using electrons as a wave. A scanning electron microscope or a transmission electron microscope. What's the difference in the two? An electron transmission microscope, you're having electrons that hit a surface and go through and you measure them on the other side. The scanning electron microscope, you're looking at backscatter. But in both cases, you're firing electrons at your sample. And you might say, why would I want to fire electrons at my sample? Why not just use light? We can make a visible microscope. Why use an electron microscope? Any ideas? The what? Just say it. It could be right, it could be wrong, though. At least I don't care if it's right or wrong. I care what you're thinking. What? Okay, magnification. It turns out that you can probably get similar magnifications for both. That's a good idea. Is that what you said as well? Okay, she said contrast maybe. What are you saying?
Change like the object or like what you're looking at.
It does change the object, it turns out. I'll mention that. The actual answer of why we want to use these. Hello? That's Larry 1R Taylor. How you doing, Larry?
I just want to say hi. We're wandering around for the weekend.
He's a graduate of Union College. He was a colleague at PHYS when I taught there.
This guy knows nothing about physics.
He knows this. His daughter took physics from him.
He acts like he does, but he doesn't know anything about it.
Let's see that.
Sorry to butt in.
Yeah.
He actually knows a lot about physics. You know.
He's a business, or probably retired now. He was a business professor there at PHYS. What were we talking? Oh yes, the electron microscope. The reason actually we use electron microscopes is the resolution. Remember we learned about diffraction and the wavelength, and we have diffraction limits on our resolution. So you have to do, I think, a few problems on that. The shorter the wavelength, the smaller the details you can resolve. So using an electron microscope, you can use shorter wavelengths for the electrons than you can get for visible light. Hence, you can get better resolution with the electron microscope. Now, to use the electron microscope, you actually, well, my experience is exclusive with the scanning electron microscope. I had to use that in graduate school. And for the scanning electron microscope to work, you need to have a conducting surface that the electrons are hitting. So in my case, I was studying magnesium oxide and sodium chloride. Those are not conductors of electricity. A lot of people use this for biology. They're studying some little tiny insect. Once again, not a conducting surface. So what do? We vapor coat them. We vapor coat them with something that will form a very thin conducting film, gold. So I would go down and I would take my sample and I'd put it in this chamber, and then I would suck out the air, so it's pretty much evacuated, and then have a little cauldron with a little gold in it, and I would melt that gold. Some of it would sublime, well, yeah, because it wasn't boiling, go into the gas phase, and then when it hits the surface, it sticks to the surface, and I coat it with gold. And then I shoot at it with electrons. Now you think about that, and you're like, wow, isn't that expensive? Well, I'm sure it is if you do a lot of samples. I didn't have to pay the bills. You hit that with electrons, and then you see pretty pictures. And I have lots of pictures in my PhD dissertation of these samples I took with the SEM. Funny thing though, when you want to get better resolution, you have to change the wavelength. And so I'd be sitting there changing it. By changing the wavelength, I'm changing the energy of the electrons. Change it this way, that way, get a beautiful picture, and all of a sudden the picture would go and bloom and just have a big bright spot. And the idea is what happened when I got the big bright spot? I had just burned a hole through my gold because I was hitting it with these high-speed electrons. And that's very disappointing because, that sample's now damaged. And so, I wasn't a pro. I was a graduate student. You got to cut me a little slack. And so you can see here some pictures that you might take with these. This is a transmission electron micrograph here and a scanning tunnel electron micrograph here of some insect's mouth or I never want to deal with. Right, so we use these because we can get better resolution. Something else that's interesting to note, you need lenses. So you have a cathode that's, okay, I have a picture, that's emitting the electrons. And then you have a coil here, because that coil is going to create a magnetic field, and that magnetic field is going to cause moving charge to have a force. And so you're creating a force there that's going to focus your beam. So you're making lenses out of magnetic fields. So that's how you're doing your beam focusing is with magnetic fields. And yeah, here you're looking at the light that comes off. So a lot of physics that we've learned this semester goes into using those electron microscopes. Now, once again, this is super important. What? Not that question. You can answer approximately now. What is the key idea of Louis de Broglie's hypothesis? Okay. We have some numbers we're switching around there. So we had 13 for one answer, and then we had essentially one each for the rest. So there's only one answer here. I said it many times. 13 people picked it up. Electrons have both a particle and a wave nature. Everything we've been talking about today, it turns out, has been that one thing. That electrons have both a particle and wave nature, and that we can see it and we can observe how it works. So quantum mechanics builds on that. Now, what I do not have here is anything that has to do with the wave function. For the people in my Physics 252 class, we started with the wave function last week, and we're going to continue and find the wave function next Tuesday. There are two approaches to quantum mechanics. One is the wave method that we've been talking about, and we are going to come back a little bit and talk about it, I think, a slight bit more. And one is linear algebra. Linear algebra is basically making matrices and vectors and organizing the properties. Werner Heisenberg was the person who started that area. Erwin Schrödinger was the person who started the area of, let's do it as a wave equation. And Heisenberg came up with this Heisenberg uncertainty principle that says the uncertainty in the position of an object multiplied by the uncertainty in its momentum is always going to be greater than or equal to 1/2 of Planck's constant divided by 2 pi. Now, in quantum mechanics, Planck's constant divided by 2 pi is ubiquitous. It is everywhere in quantum mechanics. It's the unit for angular momentum, for starters. So we take this h over 2 pi, Planck's constant divided by 2 pi, and we define a new constant. Some people still call it Planck's constant. Some call it Planck's reduced constant. I'll just say h bar, but this h with a bar means Planck's constant divided by 2 pi. And so this uncertainty, the product of the two uncertainties is always greater than or equal to Planck's, or h bar divided by 2. Now when you read this, it carries virtually no weight. So if we go back to things that make sense to us, if I have a wave that goes through a slit, my uncertainty in its position would be the width of that slit. Well, divided by 2, I say it's at the middle, plus or minus half of the slit width. So that's what my uncertainty in position is. But as it goes through the slit, what's going to happen? When the wave goes through the slit, it doesn't stay in this space. What does it do? It diffracts. It's going to spread out. And so I'm going to have it spreading out, and because of de Broglie's relationship, that momentum is h over wavelength, my uncertainty in momentum would be my uncertainty in its direction it's traveling. And so I can say, well, if it has a smaller wavelength, then that means it's going to diffract more, and I'm going to have less certainty about the direction it's traveling. So my uncertainty in the momentum is going to get bigger if the wavelength is smaller. And so we can look at the relationship between the width of the slit and the amount that it spreads, the uncertainty in the wavelength or uncertainty in momentum, and see that there's always going to be some relationship there. And Werner Heisenberg did the careful calculations to show that the uncertainty in momentum times uncertainty in position is always going to be greater than h bar over 2. Now, putting this into a practical sense, if I am driving my car, I have a certain uncertainty in my position. how big is my uncertainty position when I drive a car?
Less than 1%.
It's what?
Less than 1%.
Less than 1 what? Okay, less than 1%. My uncertainty position is really small. I could probably determine my position, using GPS, it would be somewhere around a meter probably or less these days. Using other things, I could determine it much more accurately. So I can maybe determine the position of my car to, let's say, 10 to the minus third meters. Right, that's a pretty accurate position of the car. Then we have the uncertainty momentum. According to this quantum physics equation, my uncertainty position times the uncertainty momentum is going to have to be greater than or equal to h bar over 2. H bar over 2 is very close to 1 times 10 to the minus 34. So if my uncertainty in position is 10 to the minus 3, that means my uncertainty momentum is going to have to be greater than or equal to 10 to the minus 34 divided by 10 to the minus 3 is 10 to the minus 31. Well, that means my uncertainty in speed is going to be my uncertainty momentum 10 to the minus 31 divided by my mass of the car, let's say 1,000 kilograms. Does that sound right? That would be a 2-ton vehicle. So divide that by 1,000, I'd be back to 10 to the minus 34 for the uncertainty in speed. Well, I'm not going to care about uncertainty in speed at 10 to the minus 34. I'm not going to be able to go to traffic court and say, but Your Honor, I was very carefully measuring my position, which meant my uncertainty in speed was 10 miles per hour. Right? It's not going to work out mathematically. So on an everyday basis, the uncertainty relation doesn't affect us. But if we're working with really tiny things, it starts to actually have measurable differences. So, what's his name? Gamow. George Gamow wrote a series of books to try to explain science. And in one of these books, he has a person that's riding around in a world where, like, the speed of light is 35 miles per hour. If the speed of light is 35 miles per hour, is relativity going to affect you? On an everyday basis, you ride your bicycle and you're going 12 miles an hour, you're going about 1/3 the speed of light. If you're going 1/3 the speed of light, you're going to see length contraction. As you're riding through town, you're seeing all the buildings are contracted. You stop and they get longer. Very bizarre. And what about with this here? If Planck's constant is a much bigger number, then you would start to have to worry about this uncertainty relation on an everyday basis. But it's because of how small that constant is, how big the speed of light is, that we don't worry about these situations on an everyday basis. Just a historical note about the brilliant Werner Heisenberg. The brilliant Werner Heisenberg was Germany's oh no, I can't remember his name now. Who's the guy who led the Manhattan Project? That commie pinko. I honestly can't remember his name suddenly, which is really bad. The person who headed the Manhattan Project, he'd always, what was it? Yeah. Oppenheimer, he'd always actually had socialistic sympathies. But as long as he was leading the Manhattan Project, leading the U.S.'s search for a nuclear bomb, that was okay. And he did a very good job of guiding the most brilliant scientists to make a nuclear bomb. Now, we're going to talk about this later, but I'm just going to do my little soliloquy now, and when we get to it later, I'll just remind you of it. Why did the Americans build an atomic bomb?
It's not ours to ask why, but why not?
Well, I'll kick him in the shins later. The Americans built an atomic bomb because the American scientists noticed that Germany stopped sharing information about nuclear research. And Germany started an embargo on shipping out certain radioactive materials. And the American scientists realized that there's a lot of energy available due to that E = mc² relationship we talked about. And they said, the Germans could be trying to weaponize this new idea. And so they wrote a letter to the president. They had Albert Einstein be the primary signature because of his importance, saying the Germans are going to destroy us. They're building a bomb that could destroy everything. Everything. And we need to do the same thing so they won't use it against us. And so the Americans started the atomic bomb project. And everyone, all of the scientists of note, were on board because they all had the belief, if we don't do this, our way of life will end. It will be, Hitler's draconian rules that will be involved, and we don't want that. So they built this atomic bomb. It went boom. The U.S. dropped 2 atomic bombs on Japan, one in Hiroshima, one in Nagasaki. And the Japanese were appropriately aware of just how devastating it was now. They surrendered, and the war was over. The Germans did not ever complete their nuclear bomb. As I understand, it's because Hitler didn't trust the Jews. And a lot of the top scientists were Jewish. And so he didn't trust them, and they kind of stopped the project. So we can have Hitler's racism, I think, to thank for not having a nuclear world war. He's the one that was leading the project, Heisenberg. After the nuclear bomb, that was a nuclear fission bomb, was created, scientists quickly realized there's a lot more bomb you can make if you make a fusion bomb. And so the government asked Oppenheimer to get the old band together and make a new bomb. But the scientists who had made the first bomb now stepped back and said, wait a minute now. We made something that's terribly destructive. You have to have a conscience. I don't care if you're going into medicine, if you're going into being a plumber. You have to have a conscience. You have to be aware of the good and the bad you're doing. And the scientists were only thinking of preserving life and our way of life. That was a good thing. But then they saw it used, they realized this is really a bad thing we created. And so Oppenheimer, along with many others, said, no, I'm not having anything to do with that. Oppenheimer was actually ostracized then for his socialistic leanings. So they're like, you're a commie pinko, that's why you won't make us another bigger bomb. And they found other scientists who were willing to do that. And so we do have atomic bombs that are now fusion bombs. It didn't take long to get there. The fusion bomb has a much bigger damage effect. And, well, just on one last note, the North Koreans haven't detonated a nuclear bomb in months now. Of course, nobody knows the official reason why, but you know what the most likely reason is?
Yeah, because Trump is his friend.
No. I think that his agreement to meet with Trump is simply because they can't. They can't because they were doing their detonations under a mountain. And every time you do the detonation under a mountain, of course, the mountain goes poof. And they caused so much damage to the mountain that it collapsed in on their facility. So they don't have a facility for testing their nuclear bombs. So they have to rebuild infrastructure before they can do the testing. So, yeah, let's talk to President Trump while we can't do anything and see if we can get some concessions for you. Anyway, that's it. Political conjecture. Have a great day. Enjoy the alumni weekend.